So Mahdi is our next speaker, and take it away.
Okay, hello everyone. I'm Mahdi Ghorbani, a PhD candidate of University of Edinburgh, and today I want to present our paper, Compiling Structured Tensor Algebra, to you. So let's start with the motivation of this work. Tensor algebra basically lies in the heart of many, many applications like machine learning, deep learning, quantum computing, and signal processing. And these tensors are usually structured in some way or another. So they can be dense or they can be sparse, as in they have like several zero elements in their structure. And there are tons of frameworks working on providing efficient code for both sides of the spectrum. Like for dense computation, we have TensorFlow, PyTorch, NumPy, a lot of frameworks providing efficient code generation. And we have Taco, SciPy on the other side of the spectrum, providing good infrastructure for sparse representation. And when we move towards the dense side of the spectrum, we get more specialization opportunities. Like we have better vectorization, parallelization, cache locality. And when we move towards the sparse end of the spectrum, we have more flexibility. And we get a lot of benefits, like better storage, better and smarter algorithms that have lower computational complexity, and we can scale them to larger size of data and larger size of tensors. And we observe that in so many cases, we have other form of structure that is some form of like crossover between dense and sparse. So it's basically sparse, but it has like some nice form of structure that we can capture it symbolically. And they appear in like machine learning and signal processing as I go to them through this talk. And our main focus is on this type of structure. So let's start by what we mean as structure and how we can capture it. So here, for example, we have a diagonal matrix. And it's a 4x4 matrix, and it's very sparse. So if we want to capture it, capture this diagonal, these unique elements, in a set, we can represent it in this format. So if we put x between 0 and 4, y between 0 and 4, and x equals y, it basically captures all the non-zero elements. And we call this a unique set. So basically, unique set is all the non-zero elements, and we just ignore the zero elements. And it would be very nice if we can do some structural reasoning, meaning that if we can propagate that structure throughout the whole tensor algebra computation. And let's see what we need to do that. So first, we need to represent the tensor algebra computation over this matrices. And it's basically matrix-matrix multiplication. So we have T of x and z equals to m of x and y multiplied by v of y and z. And we represent the structure of the inputs. So as we had in the previous slide, the structure of both of them are diagonal. So they're represented as x and y between 0 and 4 and x equals y. And structure of v is basically the same, y and z between 0 and 4 and y equals to z. And what we want to know is what is the output structure. But for this, we need a better representation. This set representation is not ideal to define some form of automatic structure inference on top of them. And we cannot easily propagate the whole structure throughout the tensor computation. So for that, we defined a better representation based on using the same notation as tensor algebra to cover it. So here we have the set representation of this diagonal matrix. If we just do a mapping from false and true to 0 and 1 and transform the conjunctions to multiplication and disjunctions to addition, we can reach to this other representation, which is very similar to the tensor algebra input. And it's going to be x between 0 and 4 multiplied by y between 0 and 4 multiplied by x equals y. And these two are corresponding to each other. So if we have this representation, now let's go and do the structure reasoning and find out what is the output structure. So for that, we have a full set of structure reasoning rules, structure inference rules in our paper. And this is just one example of a generalized version of one of them. And it says if we have a multiplication of two tensors and the set of variables in the input tensors, the union of them is equal to the output variable, the set of variables of the output tensor, then the unique set of the output is going to be basically multiplication or conjunction between the unique sets of the inputs. So here we just put the structures, put the unique sets in the formula So the two matrices are diagonal, so these are the structures, and we multiply them, and as expected, we get the diagonal as the output structure. But is this the only interesting structure out there? The answer is no. So if we have something like redundancy structure, what do I mean by redundancy? Here, for example, we have symmetric. And in symmetric, if we take a look at the upper triangular part of the matrix, we can basically capture the whole elements. Like basically the lower triangular part is the same as the upper triangular part if we have a proper mapping from the lower triangular part to the upper triangular part. And here we change the definition of unique set and take it a bit more literally, and we only keep the unique elements in the unique set. So it's non-zero and it's unique. So here we chose to select the upper triangular part as the unique part. I mean, we could pick the lower triangular part, but here we just picked that. And we have a redundancy map. And this redundancy map basically provides the proper mapping that we needed. So it has double the number of variables of the original tensor. And the conditions over the first two tensors are representing the area that has the redundant elements, here the lower triangular part. And the conditions over the last two dimensions are basically representing the mapping that we need. So here, if we swap x and y, we can basically find the unique elements that we want. We can retrieve all the elements. But the question is, are all the structures this simple and easy to capture? The answer is no. Imagine we want to create a covariance matrix for polynomial regression degree 2 over a vector of size 4, very tiny vector. And this is the output. It's going to be a 20 by 20 matrix, 400 elements. Only 65 of them are unique. As you can see in the right-hand side figure, only the black elements are the unique elements, and the rest of them are just repetition, and we can just capture them through our redundancy map. So let's see how we can do that, how we can capture this nice structure there. So for that, we need to have an intuition on how we create the covariance matrix first. So basically, for creating covariance matrix, we have a vector x, and we do x transpose, or self-outer product of x to itself. And x for polynomial regression degree 2 is going to be a concatenation of a vector called f and the linearized version of self-outer product of f to itself. And we just replace this value to the formula, and we can see that we can only compute m1, m2, and m3 to capture all the elements. And m1 is corresponding to the top left part, m2 is the rectangle on top right, and m3 is the square on bottom right. And the rectangle in left right is, in bottom left is basically equivalent to m2, because covariance matrices are technically symmetric. So as long as we have a redundancy map, we're good to go. So to know how we can do that throughout our architecture, our framework, we need to know a bit about the architecture of our framework. So our system takes tensor algebra and the input structure of the inputs as an input. So we have basically tensor algebra computation. We have the structure of all inputs there. And then we have a structured tensor unified representation. And why it's called unified representation, I'll go through that later. We pass it through STUR, and it does structure inference. And what is structure inference is basically what you've seen in previous slides. We propagate the structure of the inputs throughout the whole tensor computation. And we infer the output of the structure of the output. And the next step is optimizations. We do some level of optimization over the inferred structure. And the very last step is code generation. And we generate C++ code, structure over C++ code for the tensor algebra computation. So let's go back to the example that we had. So because of lack of time, we just focus on M2, M1, and M3 can be computed in the exact same way. So as long as we know how everything happens for M2, we're good to go for M1 and M3. So let's see how we can generate code for M2 and for M2. So M2 was this mathematical computation. First, we need to translate it to tensor algebra and put it as an input to STUR. So the translation is going to be M2 of INCOL equals to self-outer product of f 3 times to itself multiplied by column equals j times n plus k, which is a linearization condition because we want to fit everything in a matrix. It's the vec in the mathematical notation. And some of you might wonder how we are doing like a multiplication between real domain and Boolean domain. So here, basically, the self-outer product, which is the actual arithmetic computation of this tensor algebra computation, is going to be separated inside STUR and from the Boolean domain, and it's going to be used in the code generation. So basically, we write it in this way. We multiply all real domain and Boolean domain to do the structure inference properly, do optimizations properly, and in the end, most of the Boolean domain, which is the computation over indices in our computation, is going to end up in unique set and redundancy map, and the real part is going to represent the actual arithmetic, and it's going to end up in our generated code. So we separated later, but STUR treats them properly, and basically in Boolean domain we translate them to conjunction and disjunctions. In real domain, they're just what you see there. And the second input that we have is the structure. So the structure of vector f here is x between 0 and n, and we take that as input. And now we want to do structure inference. What our structure inference says, structure inference rule says, is that if we have a self-outer product of a vector by itself 3 times, we just restrict the area. Instead of like iterating over a cube, we can iterate over this pyramid. Like we restrict the computation domain, and we write it as this part. And the Boolean part of the tensor computation is going to be appearing in the unique set as it is. And the next step is we apply some optimizations. The first one is inlining. We put the structure of f in this computation, and this is the output. The next step is logical simplification. And the I less than equal j less than equal k, and both, like all of them between 0 and n, basically subsumes the I between 0 and n, j between 0 and n, and k between 0 and n. So we just get rid of them, and we keep the last line. And we need to generate some code for that now. So we have the output structure, and we have the tensor algebra input. So we can basically use the unique set, the structure, for generating loopness and the computation over indices. So here it's for I between 0 and n, j from I to n, and k from j to n. And the index call is equals j times n plus k, which all of them are computed based on the unique set. And the arithmetic part, fi times fj times fk, is going to appear in the computational part of the code. And we've done some extensive evaluation. As an example, we have some of them here. Polynomial regression degree 2 is the example that we had throughout the slides. And as you can see, if we change the size of the vector, the input vector, from 125 to 250, we can get 1 to 2 orders of magnitude performance boost compared to PyTorch, NumPy, TensorFlow, Taco, and all of them have like very optimized kernels down there, but we can outperform them because we are structure aware. And MTTKRP is another kernel which is used for tensor factorization. It's very important. And in this case, we get between 1 to 4 orders of magnitude performance boost. And there is another important kernel, convolution, 1D convolution, which is used in signal processing a lot. And there is no proper tensor algebraic representation of it. And all of these frameworks out there, they use like some sort of manual implementation, which is very hand-tuned and very optimized to do the convolution, but we transform it to a matrix into like pure tensor algebraic form using a matrix vector multiplication and the matrix is like using this variation of Toeplitz matrix, which has both redundancy and sparsity. And on the right-hand side, we see that if we use the convolution kernel using the same libraries, but using the Toeplitz matrix multiplied by a vector, then we outperform them significantly. And even if we use them, even if we use the built-in kernels that they have, we can see on the left-hand side that we are competitive or outperforming all other competitors. So if you want to know more about STUR and the full set of inference rules that we have, if you want to know the optimization techniques that we use, if you want to see the actual compilation and code generation algorithm, If you want to know the proof of soundness for inference rules and extensive experimental results, you can take a look at our paper. And in conclusion, basically, we have a framework working on structured tensor algebra, and by structure, we mean sparsity and redundancy. And in this framework, we do automatic structure inference using STUR, which is our unified intermediate representation. And we introduced StructTensor, our framework, and it does all of the automatic structure inference, optimization, and code generation. Thank you for your time. If you have any question, I would be glad to answer.
Thank you for your talk. I have a question. What kind of inputs does your system take? Do user feed tensor of numbers and your system will automatically dig out the relation between elements? Or do you require the user to program the tensors and tell your system what are the relations?
So currently, what we have is we expect the user to provide this information, meaning that like the sparsity pattern of the inputs should be provided by the user. But as a future work, we're working on like capturing all the relation, like capturing the unique set and redundancy map automatically.
I have a further question or comment. I think if you want the user to program the tensor, the user might prefer program the computation directly. Mm-hmm. I mean, maybe programming the computation requires the same efforts as programming the tensors.
I mean, I do not agree with that fact, because like the examples that I had here, they were quite simple and they were just for representation. But imagine we have like, I don't know, a function of 100 lines of code, and it's full of like, I don't know, different structure types of tensors, and the user knows the input structures, but throughout that whole computation of, I don't know, like 100 tensor algebraic computation, if they want to keep track of like each of the structures, it's going to be much, much harder, and they can't automatically, have all of that. It's going to take a lot of effort and time.
Sorry. Thank you.
Yeah, no worries.
Let's take a question from you.
Thanks. Wonderful talk. My name is Pratik. I'm from NUS. I was wondering, I mean, you're computing these covariance matrices as you go along, right? Mm-hmm. And this computation for a very long time is like it performs really poorly with increasing dimensions, right? Say order of d cube, where d is the dimensions, right? So did you run into this issue, like when you were trying to scale up these, your benchmarking on larger and larger? Today we use very high dimensional models, and so, what's your experience with using these large models?
So basically, I mean, let me bring the slide. So it actually takes, some time. Like it's true that it's O of n3, so we, can't do anything about that. But like basically, our framework can roughly give like 24 times performance boost. I mean, it does like the computation over like 24 times less elements, roughly. So, I mean, we are not changing it by orders of magnitude or like the complexity, but we are changing the actual runtime with a large constant factor.
Okay,
so,
and the analysis time should increase, right? Like obviously
the analysis time is, I mean, it's not that long, because like basically we have a set of inference rules and we just use them, and that one doesn't take that much time. Plus that's in compilation time, so we just do it once and then that's it.
Okay, thanks, wonderful.
Maybe a quick question there while the next speaker is setting up.
Hopefully quick. So if I understand correctly, the storage you use is compact, right? You just store a vector and it represents the whole covariance matrix, right? Mm-hmm. But it seems that there's a certain maybe subclass of sparsity patterns where that is possible or that you recognize. So my question is there some kind of theory for your optimization techniques so that you stay within that class of sort of things you know how to store?
Oh, okay, good question. So here, we actually do not store everything in one vector. Like basically, we keep the structure as dense, like a multidimensional array, and we perform the computation over only the parts that they have the elements. It's going to be our future work that we're going to, have an optimized and efficient
just store
storage.
the diagonal and don't worry about it.
Exactly.
Okay, got it. Thanks.
Let's thank the speaker again. And